In this video, we're going to talk about rejection regions, sometimes they're called critical regions, and how to find them for a hypothesis test. And we'll look at all three types of rejection regions. So first, what is a rejection region? Specifically, it is a section of a normal curve, or maybe a t-curve or a chi-square curve. For those of you who've done some more work with the curves, it's a portion of the curve that defines what is really far away from the mean of the distribution. So it's basically an area, and it's cut off by a couple of endpoints, or maybe just one endpoint. The purpose of a rejection region is to decide when we should reject the null hypothesis, because if we are gathering data that's close to the mean, we should get a test statistic that's kind of close to the mean. So if we're getting a test statistic that's really far away from the mean or from the proportion, the center, we are likely to say, hey, this proportion doesn't look right, it falls too far from the center, something's up. So let's reject the null hypothesis. The size of the rejection region is based on your level of significance. So the symbol for level of significance is by this Greek letter, alpha. So A-L-P-H-A, that is your Greek letter, and that's what we use to say the level of significance. Some common levels of significance that you'll find: 0.05, that's a 0, 0.10, 0.01. And you'll notice that these are kind of similar to what we've done with confidence intervals. 95%, 90%, 99%. These are all common values for your level of significance. And so it's going to be like finding critical values in a way for those confidence intervals. Another thing that the level of significance tells us is the chances that we're willing to make of making a type 1 error. So let's look at an example here. I'm using the same example from another video. Let's suppose we sample 1,000 students who began post-secondary education in fall 2009, right around the ending of the Great Recession. According to the report above, which I did not link to, 52.9% of those surveyed have completed their college schooling at a 2 or 4 year college within 4 years of starting college. So in other words, just over half of these students have actually finished their school in 6 years. Is it possible to conclude that more than half of these students have completed college within 6 years of starting? Test the claim at the 5% level of significance. Well, let's get rid of that. All right, so what did I want? I wanted to highlight this. Test the claim at the 5% level of significance. This is how we're going to figure out our critical region. So 5%, this means we're using alpha equals 0.05. That's just one part of the puzzle for finding our critical region. The other part that we need is what side of the distribution are we working with? Because I see that word more than half, that's telling me that I need to do a right-tailed test. So here are my two clues. I have a right-tailed test, alpha is 0.05. So now I can go ahead and draw my normal model, approximately. Here is the center. And since I want the most extreme right 5%, that means that this region up here is going to be my critical region, my rejection region. Since this is a standard normal model, that's where we base everything off of standard normal. 0 is in the center, and we need to figure out, well, what is this z value? That is 0.05. So here was alpha equals 0.05. And what is this z number that is going to cut off that upper 5%? Well, if you remember watching the video on finding critical values, this is exactly a critical value. Critical value, critical region, you can see how those tie together. So this 0.05 area, it matches with a critical value of 1.645. So watch that critical region or critical value video, and it'll tell you how to find this 5% up here. So the critical value, 1.645, that's going to be that cutoff for the test statistic. Any test statistic that lands up over here above 1.645, we will end up rejecting our null hypothesis. Now, are you going to be actually getting a test statistic of 1.645? It's very unlikely. You might technically actually say if you land exactly on 1.645, you'll reject the null hypothesis too. All right, let's look down at another example. Is this 52.9% a change, I'm going to emphasize that, from 56.1% of students who started college in fall 2007 and completed within 6 years? Test the claim at a 5% level of significance. So our two facts here, we have a change. So that is going to mean that we have a two-tailed test. And alpha is still 0.05. I'm going to use the same alpha for all of these because I want to be able to compare and show you the differences. So I'll start with my normal model. Since I'm working with proportions, I know that if I meet all the requirements, I can use the normal model. So I'm assuming that that has happened. Here's standard normal centered at 0. I have a two-tailed test. So that means that I'm going to be shading two separate regions. I have two places that are extremely far away from the center because I'm looking for a change in proportion. I don't care if it's higher or lower, but anything really extreme will cause us to reject the null hypothesis. So now I'm going to bring in the 0.05. Because I have two regions, I need to take alpha and divide it by 2. So I'm going to get 0.025. That means that this area is 0.025. And this area is 0.025. So technically I have two critical values for my critical region. Now this might look kind of familiar. If you have 5% in total tails, that puts 0.95 in the middle. That's like a 95% confidence interval. So our critical values are 1.96 and then negative 1.96. So sometimes we write it as z equals plus or minus 1.96. You have two of these regions. If you're extremely high or extremely low, this will cause us to reject our null hypothesis. And lastly, let's look for those keywords. Is this 52.9% less than 56.1% of the students who started college in fall 07 and completed in 6 years? Test this claim at a 0.05 level of significance. So we're going to go back and we have another normal model because I've checked all my assumptions ahead of time. Let's say standard normal here is centered at 0. That word less than, so those are some of our keywords. That means we're going to have a left-tailed test. I want to see if I'm less than 56.1. So this region on the left side, this is my rejection region. And the area that tests the claim at 0.05, well, 0.05, that's the area of that rejection region. The most extreme 5% of sample proportions fall in this region. And what is that z value? Well, since I've done these two other problems, we can actually work smarter instead of harder. If I go back up to the beginning here, 0.05 on the right side has a critical value of 1.645, and if I just flip it to the other side, remember this distribution is symmetric, so I have 1.645, but negative 1.645. And let's write this a little bit better here. Negative 1.645. So we have a left-sided, we have a negative critical value. Any test statistic landing in that region would say, hey, reject the null hypothesis. So now I'm going to point out these differences and similarities. All three problems had a 0.05 level of significance, but we had different critical values. And that was because of the tail of the test. It made a big difference. When I had a one-tail test, left side, when I had a one-tail test, right side, I had the same 1.645. They were just opposite in sign. But when you have a two-tailed test, you're splitting the area. So instead of 5% per tail, now you're at 2.5% area per tail. So you have to scoot further out to the side so you get a larger test statistic, 1.96, and then also a much smaller, negative 1.96. So 0.05 level of significance, look for that first, and then go for which tail of test you're doing. And I use 0.05 just because, but problems may vary. Again, they might be 0.01 level of significance, 0.1 level of significance. You just have to read the problem and maybe look for a symbol called alpha.